So, first of all, I'm really happy to be here, and it's somehow a gorgeous day to be here. And already met some really nice people that I hope to continue to be friends with. I'm going to talk about a topic that is, I think, somehow everybody I know, everybody, not just academics in universities, but people on the streets and kids and just anybody have opinions about. They all have to face chance and luck and free will and the very many various aspects of randomness in our life, in our in what we read and so on, which is great, and it's also great sources of arguments and controversy, which is also great because I think they are enriching. Also in the sciences and mathematics, randomness has a long history. People started philosophy and physics. People started studying it centuries ago and debated its meaning, had definitions for it in mathematics, in probability, in statistics, and other fields. It's people looked at entropy and other notions that are related to randomness. And so there's a wealth of directions to look at this notion. And the story I'll tell you today is sort of a high-level summary of work that's been going on in about the last 3 decades in computer science, the theory of computation, and what we complexity theorists think about this, how we view it, what's its meaning and importance to algorithms and computation. And you'll see that in some senses it's a very different take on this notion than what everybody else has said before. And in some ways, I think it's very informative and useful. So let me start. It's a big audience, but if you feel you really don't understand something and maybe you are not alone, just ask me. Okay, so just to set the base, people have been talking about all sorts of randomness in all sorts of situations. I'm going to talk only about discrete events. The basic random object, random event for me will be a coin toss, which is unbiased, 50-50. Okay, and we will. This will be like perfect randomness, which will be our like gold standard. And you have many of these. So you have independent tosses of a coin. That's a uniform distribution. That's what I will call perfect randomness. So just to make sure you are all with me, here are 2 sequences of 20 coin tosses. Which one is more probable in this? Okay, very good. So we are all. So both have probability exactly 1/2 to the 20. They are equally probable, and that's what I want you to remember. That's a basic, that's a uniform probability distribution or full entropy distribution. Okay, so there will be 2 parts to the talk. The first part, I'll talk about the amazing utility of having random coins like that. You'll see lots of examples. And when we are done looking at these examples, we'll ask about whether, are all these applications of randomness real? I mean, do we actually have access to the uniform, to perfect random coins? And to answer this, we'll start talking about pseudorandomness. And I'll have to define this, but roughly speaking, these are deterministic structures. No randomness at all. Deterministic structures which share some properties with random structures. And we'll see examples and applications of these. And eventually I'll get to relate this to the to the question about where do we get random bits for the other experiments. We'll discuss what happens to all the applications of randomness if there are no random bits. Or maybe there is some randomness in the world, but it's not available in this perfect form. So we'll discuss that. Okay, so I want to start with this set of examples, and in all of them, I'll remind you this figure will appear that you always should, in the back of your mind, worry about, is this application real? Where do we get the randomness from? Okay, so the most, there's no better example to give before an election. One of the most ancient examples of the power of randomness is just sampling. You want to know, there are a bunch of people and they each have an opinion, red or blue. You want to know what they think, and one fundamental way to do it, rather than going and asking everybody, is to pick a random sample. Like in my example, it's 2,000 random people, and by random I mean drawn uniformly at random, so every set of 2,000 is equally probable. Under this assumption, this is something you can do with random bits. If under this assumption there is a fundamental law of large numbers saying that this sample with extremely high probability, 0.99, will be very informative. The percentage in the sample and in the whole population will differ, let's say of reds, will differ by at most 2%. And this theorem is easy to prove, and in fact it's a much more powerful theorem than stated, because it does not depend at all on the number, the size of the population, right? It works equally well in China, it works equally well if every planet or every star in the universe was voting, right? So so I think even though it's simple and you learn it, early in college, it's one of the most powerful theorems in mathematics, this law of large numbers, one of the most useful in life that you can sample. And here I just want to remind you that its practical use, it's if you wanted to do everything deterministically, even to estimate within 2% what is a fraction, you would have to ask all but 2% of the population. So it would be much worse than 2,000. Okay, so, and of course you can improve this accuracy and confidence by increasing number. So that's the most basic application, and I'll move to more sophisticated, more recent ones. The probabilistic algorithms are the main users of randomness. Here's an example. In this example, this is called imagine you have a region in space. Here the region is square, but it can be of any shape, and you want to tile it with dominoes. Okay, so this particular picture shows you one domino tiling. You can ignore the colors. It's one domino tiling, and of course there are many ways to tile it with dominoes. The question is how many. Estimate how many. This is a monomer dimer problem. It's a physical problem. It's if it comes from having diatomic molecule material. And this count captures fundamental properties about this material, like free energy and related to computing phase transitions and stuff like that. So anyway, it's very important to be able to estimate this number. And the obvious way, I mean, there are actually, if it's an n by n grid, or if there are n squares in this shape, the number of possibilities is exponential in n. So you're not really going to try them all, and it turns out that this very beautiful and important algorithm has an extremely fast probabilistic algorithm for approximately counting the number of tilings. It goes by the general methodology of Monte Carlo simulations, which is very old. Started with the Manhattan Project, actually. But anyway, it's a probabilistic algorithm. What's a probabilistic algorithm? I want to, by the way, if I'm using any jargon you don't know, ask me. It's just a piece of software. It's just a computer program that is allowed to take these random bits as extra input. That's a probabilistic algorithm. So using randomness, there is an algorithm which does it very efficiently in polynomial time, very quickly, whereas if you wanted to do it deterministically, at least as far as we know, you would have to enumerate all possibilities, namely run in exponential time. I want to stress that that's just as far as we know. It's quite possible that one of you will discover a deterministic algorithm to do it tomorrow, a fast deterministic algorithm to do it tomorrow. It's possible, but we don't know. There is an exponential gap. And this exponential gap actually appears in in numerous problems. I listed here a few that are for mathematics, but you know, they're of course in optimization and they are computer science and logic and lots of. So, for example, finding a large prime. I ask you for a 1,000-digit prime. Nobody has any idea how to do it in or n-digit prime. Doing it deterministically seems to take exponential time, right? Finding one, not deciding whether it is. But probabilistically, there's a very easy probabilistic algorithm. Factoring multivariate polynomials is another one. Approximating the volume of high-dimensional convex sets is another one. All of these are quite sophisticated probabilistic algorithms. Computing Fourier coefficients of multivariate functions, etc. For all of them, what I said before is true. We have very fast probabilistic algorithms with randomness, and without randomness, the best known algorithms require exponential time. Okay, so randomness seems extremely powerful in this domain. Okay, so let's move to other. Everybody happy?
Why is finding large primes hard deterministic?
Why? Well, you have a fast way to do it? No, seriously. I mean,
why can't I just systematically look?
It will, and
you tell me how many digits I'll start at.
Yeah, n digits. Yeah,
I'll start at 10 to the n and just keep adding 1 till I get a prime.
It will take, well, as far as we know, it will take you exponential time. There are exponential in n many numbers of length n. Right?
Right, but the first prime will come pretty soon after log n.
Well, nobody knows that. No. Oh, they would love to know this, but they don't. It's an open question. Yeah. If the mathematicians got their act together, I would remove it. I would remove it. So it's, as far as we know, it's, It's some power of capital N, of power, not log. As far as we know. Here's another example, different than what we will later talk about, but I just want to mention it. Some things that are possible with randomness and simply impossible without randomness. Impossible. That happens in particular in the setting of distributed computing. I mentioned it two problems. Those who don't know this field should get a sense that these guys really know how to name their problems. So these are two problems: the dining philosopher's problem, which is about resource allocation in distributed environments, and the other is the Byzantine general's problem, which is about coordination in distributed systems. In all of them, there's a key element that there's no global synchronization, which makes things much weirder and harder. And anyway, in both of them, I'm not going to define them formally. I just want to tell you that in each of them, there's an impossibility result showing that if the programs underlying these distributed agents are deterministic, they never satisfy the properties that you want, very natural properties, like being able to access a resource that you want eventually. Whereas if you allow randomness, so these programs are probabilistic, then it's possible and even efficiently possible. So randomness here plays an absolutely crucial role. Okay, so that's another example of the power of randomness.
Can I make another comment? So for me, this one it's really using randomness to break symmetry.
Absolutely. This is
it's sort of an artificial to imagine you didn't have that you really had symmetry to begin with.
Yeah. So. There are lots of situations where real life situations where it is absolutely true that A, you have no synchronization, and B, you have symmetry. When you, I mean,
everybody has their own number, I think. So I don't think there is symmetry.
Well, how do you call this? Not cellular network, where they just throw a zillion measurement devices in, sensor networks. You can have a number for each one, but if their conversations needed to depend on their number, then you wouldn't really be using them. There are lots of situations where, but it doesn't matter. Let's say it's a nice math problem, which for me is enough. Yeah, but it's true that randomness is often used to break symmetry, but in many of these protocols it's far than enough of use. It's an essential part, but it's far than enough. So even with symmetry, sometimes randomness is essential. With asymmetry, yeah. So it's just the two examples I chose. This is true. Okay, so now I want to give you two further applications where it's not about doing something, it's even defining things. Sometimes it's essential to have randomness. Okay? Game theory is one fantastic example. So here's a typical game that they study in game theory. This is a chicken game of woman. You have two players in this case, and each of them has two strategies, being aggressive or cautious. This game is supposed to, you either too much of drivers are driving towards each other, and whether they will be, swerve to the side, being cautious, or continue hoping the other guy. And then these are their payoffs. So to the black player and the purple player, according to which choices they make. So maybe this should be minus infinity. But anyway, you describe this sort of matrix of payoffs, and the question is, in general games like this, what is rational behavior in these strategic situations? This could be companies or governments or whatever. What would be sensible? What would be rational? And a good definition that's maybe the primary still in use was given by Nash, his award-winning definition, is that rational behavior should correspond to stability. A set of strategies for these players is stable, is a Nash equilibrium, if given what the other is doing. It can be with more players. Given what the choices of the other players, I should not deviate from mine. It's sort of a stability notion. So that's there's no incentive to deviate given that others are keeping it. So if somehow everybody got a message, please use these strategies, nobody will have a reason to deviate. Now, Nash didn't get his Nobel Prize just for this definition. As you know, he got it for his theorem. And Nash's theorem says that every game, so this is not a, obscure definition. This definition, this property, is shared by all games. Every finite game, no matter how many players, how many strategies to each, there is always a Nash equilibrium, such a stable solution, which is great, but the theorem doesn't end there. It's a theorem assuming that the players are allowed to randomize. They are allowed to use mixed strategies. So in this game, for example, there is no pure strategy solution, but if both players, there is a unique Nash equilibrium, if each of them chooses to be cautious with probability 3/4 and aggressive with probability 1/4, then it is an equilibrium of this. So with randomness, there's always Nash equilibrium. Without it, there are many games that just don't possess such solution. So it's another sort of different application of randomness, important one. And there's, of course, another one that you are all familiar with. This is just cryptography. The very notion of a secret cannot exist without randomness. I mean, you try to define it. There is no definition for it, and Shannon first built this theory where he defined, all the notions of information theory and entropy, and talked about the secret is basically as good as the amount of entropy in it. So if it is picked as a 9-digit, if you pick your password as a 9-digit number, then my probability of guessing it is 1 in a billion. If you pick it randomly. If you pick it just a random phone number of your friend, and you have, I don't know, 20 friends, or let's say on Facebook, maybe you have 200 friends, it's still, my chances of guessing this number are much higher. So anyway, randomness is essential for definition of secrets, and then it's essential for everything else in cryptography. I mean, I could go on list. There's no definition in modern cryptography that the ability to randomize is not essential. Okay, so they all require randomness, and there are more applications of randomness. And actually here the question of where the random bits are coming from is very important if you are playing there. So okay, I hopefully convince you that randomness is good and useful, and we would like to know whether all these applications of perfect randomness are available to us. So we want to know where are these random bits used in all these applications coming from. So I don't know about you, but when I don't know an answer to a question, I Google it, right? So I Googled it. Seriously Googled it. I got, you see, like 4 million. I just wrote 2 random bits, and I got 4 million answers. So that's where I mean, we could have guessed, right? Where do you buy it? Where do you get random bits? You buy them. These are all companies that sell random bits. Yeah. So you can buy 2 random bits. Of course, then you wonder where do they get the random bits from. So I went and read a few, and that uses radioactive decay, and another use atmospheric noise, and these last 2 use some quantum phenomena they take from photon measurements. And so they all use various physical phenomena to get the random bits. This guy, that's the most, I really wondered whether people are buying from these guys. And people are buying. This company sells quite a bit of, quite a number of these chips, generate random bits. Can you guess who were their customers? Casinos, actually. Casinos buy from them. Anyway, you can wonder, of course, what goes into this chip. You should wonder what. And there's a very recent line of work that I will not have time to talk about, how to certify, how to verify that something is actually has some randomness content, but I will not talk about this. So I want to, now that we have an issue, right? We want to know whether something is random. We obviously need some definition. And I want to talk, this is going to be the most important slide of the talk. If you get this, you don't have to remember anything else, although there are other interesting things. I need a coin. Okay, here's a coin. And I need a victim, James. Yeah, well, you as a chairman, you have to volunteer. So I'm not. No, you don't have to come. I'm not going to cut you in half. I'll just ask you 3 questions. Okay. So what I'm going to show you. Here's me, and with the coin, and here's James. And so this story is from a paper of Blum and Micali from '81, very important paper in the development of randomness and pseudo-randomness. And we are going to understand what's random, right? So I have my coin in my hand, and I'm going to toss it. And just as it leaves my finger, James should say what it will be when it lands on the floor. So there may be about, it will take a second to get to the floor, and then. So I'm actually, that's the question. So I toss the coin, and you need to guess what it lands on. And I'm not going to actually toss and check you. I just wonder what you think is your chances of getting it right. 50%. Good. Okay, so that was my first question. Okay, so let's. So we did it once. Let me change the experiment a little bit. This is a computer science department. You didn't come here with your laptop, but we can assume that some other people. Yeah. Suppose we did the same thing. You just have your laptop and maybe reading your email. Anyway, you have your laptop with you, and what do you think is the chances that you'll get it right?
1/2.
Very good. No wonder you are the chairman. right, so let's repeat it one more time. And now I give you much more to work with, right? So I give you a bunch of video cameras all trained on my finger, and they are connected to a Cray supercomputer, which is all connected to your laptop. And now, just as it leaves my finger, you should be able to, you should guess what it will land on. What do you think are the chances you'll get it right?
I would program that properly.
Well, let's say, I didn't have room for the army of programmers that are.
I don't know how deterministic the universe is, but I'll just say a half.
Oh.
One? I don't know.
Okay, yeah, well, that's my, yeah, you're right. It's a very good question, but I would say it would be very high. You know, so whether we know or not, don't know whether the universe is deterministic or not, I am willing to bet, although I didn't try it, that you know, with enough information about the humidity in the air and the distance to the angular momentum that can be quickly computed, almost surely you will be able to determine what it will be. So, but what's the point about this story? Okay, so we've done this three. But the point is not your guesses. The point is that the random phenomena might cause tossing of a coin did not change in all three of them. And this should ring a bell to you, because in all previous definitions throughout the ages of randomness, it was defined as an objective property of the phenomena. It didn't change here. What changed is the is the observer. What changed is the observer. And this is a key thing to everything that goes on in the rest of the talk and in all this study of randomness in computational complexity. That randomness is viewed like it's in the eye of the beholder, or in the computational power of the beholder. How unpredictable, how random something is depends on your computational abilities. Okay, and it is this point of view that will continue with. So, but that's what you should remember. If you want to know what changed when computer scientists started looking at randomness, this changed. It became a subjective.
I guess just
difference.
If you think this example is fanciful, there's the business of the casinos, the guys with the cameras in the casinos.
Yeah, yeah.
About that,
Yeah, but the difference with the casinos, a little bit different than the casinos, is that this is about having information. Here it's about how much computational power you have. The information James had in all three experiments.
I don't mean card counting, I mean the guys with the cameras.
Yeah, no, so the camera.
They're analyzing the situation after the roulette wheel is turned, and they're able to determine where
Oh, the guy, not the owner. Sorry, I thought you were talking. Yeah. You're right. Yeah, it's
so
being. Yeah. No, it's not fair. This is being used. Yeah, that's true. Okay, good. So is this clear? I'm going slower than I planned, but somebody will stop me when I read. Yeah. Anyway, that's a clear message. This is an operative and the subjective definition of randomness. Okay, so good. Now we are at the second part of the talk where I want to talk about pseudorandomness, and we'll relate everything in the end. So this is going to be an abstract slide, but then I'll give examples of it. So don't worry if you are not fully understanding it. But as I said before, pseudorandomness is a study of deterministic structures, and structures can be anything you want. It can be numbers, can be graphs, can be sequences, can be, I don't know, matrices, whatever, some universe of structures. So this is a universe. And now I want to say what a pseudo-random property of an element in the universe is. So I want to say what a pseudo-random property, and it's going to be very simple definition. A pseudo-random property is simply a property that covers almost this whole universe. So it's a property, it's just something which is a property of most elements I want to call pseudo-random. Okay? Why? Because if you pick a random object in the universe, it will have this property with high probability. So that's what I want pseudo-random to mean. And then there are many such properties. We'll go through some examples. Okay. But I just want, so a property that's shared by almost all elements is a pseudo-random property. And later, this pseudo-random property will really capture what these various computational devices like James in the 3 different stories was trying to do. I just want to say that pseudo-randomness is studied both in math and in computer science, and they have a slightly different angle on this notion. I mean, many mathematical questions, and we'll see examples, are about whether a particular natural structure has a particular pseudo-random property. And computer scientists usually just want to find efficiently some element with a pseudo-random property. Like a good code, good error-correcting code. It's you probably know most codes are good codes. That's what Shannon proved in his famous paper. And then building one which is explicit and usable, that's a question of this type. But despite this different attitude, so I want to say the computer science attitude of just efficiently finding one has a very nice, so just give me any object with a property, has a very nice expression that I stole from Howard Karloff, which is just the problem of finding hay in a haystack. This is, yeah, you come to the haystack, almost everything is hay, but you start picking things and there are needles. So it's a non-trivial thing. Not just finding needles in a haystack is non-trivial. It's also finding hay is non-trivial if the stack is exponentially large. Okay, so, but anyway, there are lots of joint work between math and computer science on in understanding pseudo-randomness. So it's really a very big field, big growing field. Okay, so let me give you some examples of pseudo-random properties, okay? You all recognize this number? Okay. I want to talk about normal numbers. Normal numbers so this is an infinite decimal, right? It's a number, you can think of it as a number between the 0 and 10, let's say. And I want to say when it is normal. And then I'll show you that normal is a pseudo-random property. So I want such a decimal, I want such an expansion. I want it to have the following properties. It will actually be a list of infinitely many conditions. I want that every digit appears 1/10 of the time, like you would expect in a random. I want that every pair of digits will occur 1/100th of the time. I want that every triple will occur, etc. So I want this for quadruples and so on, infinitely many conditions. And moreover, I want this to hold not just for base 10 representation of the number, but for every base. Base 2, base 3, base 20, base million, okay? So there are lots of conditions. Despite the fact that there are lots of conditions, it's actually a very simple theorem that almost all numbers, all real numbers between 0 and 10 are normal. It's a simple exercise. But anyway, because we have these properties, so almost all of them have this property, that are normal, then normal is, by my definition, is a pseudo-random property. Okay? So that's an example. We know something about these math and CS questions about this property. For example, this is something we don't know. We don't know, that's one of the more embarrassing stories mathematicians like to tell. We don't know whether pi, this number, we don't know whether it's normal, even though experiments were done to, I don't know, billions of digits and every such statistics seem to hold. We don't really know whether it's normal or not, or any other explicit number. It's just like e or square root 2 or whatever. There are algorithms, so of course it's an infinite thing, so you have to define what you mean by finding a number like this efficiently, but you can talk about finding the nth digit of this. So there are some results there. Anyway, normal numbers was just a simple way to exemplify pseudo-randomness, pseudo-random property for me, but I want to talk about other ones. This is, it's an interesting mathematical objective, but I don't know if it's a big one. So I want to show you that really important properties, important mathematical and computer science problems are problems about pseudo-randomness, okay? Not just this one. So I want you to care about this. So I'm just wondering, the students, the audience, you know, how do you know if a problem is important? You trust your advisors? What do you do? I'll tell you the answer. It's money. So here are, you know, here are problems with a good monetary value. Yeah, I hope you are not taking me seriously, but it's some indication. It's interesting, those who don't know this list, this is a list that was compiled in the year 2000 by the Clay Mathematical Institute. They had a bunch of famous mathematicians sit down and decide what are the good challenges for the next millennium, and or maybe just the next century. And they came up with a list of 7 problems. And there is a reward of $1 million for solving each. So at least these are good problems. These are important problems. Of course, if that's your way of making $1 million, you should remember that one was already done, and maybe you should hurry. Although he didn't collect the money. It's an interesting story, but beyond the scope of this lecture. What I want to talk about is 2 of these problems that should be somewhat familiar in this audience. The P versus NP problem and the Riemann hypothesis problem. One is the most famous problem in computer science, and the other the most famous problem in mathematics. I'm not saying most important, but also some would argue that. So anyway, extremely important and challenging problems that hundreds of people are thinking about. And when you look at them first, I don't think that most people would recognize them as pseudorandom, as questions about pseudorandomness. So that's what I want to explain. Now, I will do it very briefly for the P versus NP question because it's a computer science audience. Let me just say it like that. So we need a universe. The universe will be Boolean functions. We need a property. The property is that this Boolean function is difficult to compute. And most functions are difficult to compute. That's a simple argument. So it's a pseudorandom property. And the question is whether particular objects, natural objects like the traveling salesman problem or satisfiability or some one of your favorite coloring problem, whether it is in this set, whether it has a property of being hard to compute. We don't know how to prove about any function that's hard to compute. So in this sense, it's a question about pseudorandomness. What I want to show you is the same thing for the Riemann hypothesis. So let me just make a quick show of hands. How many people here can state the Riemann hypothesis? Not proof, just state. Okay, good. So a few can state it. So at least, I mean, there's another bonus of this lecture. After, in 5 minutes, all of you will be able to formally state the Riemann hypothesis, all of you. And not only will you be able to state it, you will be able to go back home and explain it to your family and friends. Okay? So if you learn nothing else. And this is because it is a question about pseudorandomness. And this is a very elegant way of formulating it. It's a question about random walk. So I'll explain it in more detail here. So I want to explain the Riemann hypothesis. For this, we have to talk about the random or the drunkard walk. So imagine there is a pub here so this is a street, and in point 0, there is a pub, and there is this guy who walks into the pub and has a few beers, comes out, and starts walking up and down the street. Okay? And probably somewhat randomly. So let's say that a step up the street or step down the street with probability 50-50. That's the definition of a random walk. Okay? And now you can study this random walk and see, you can plot it, you can do, in this case I did 10 experiments. I didn't do them, I stole them from Wikipedia. But 10 experiments of where that person will be in the first 100 steps. Okay? And one striking feature of this 10 experiments is that in all of them, even though he took 100 steps, he stayed pretty close to the pub, right? He's within 10 or 15 paces from the pub, even though he walked for 100 paces. And that's not an accident. It's a very simple theorem to prove that almost surely, so almost all random walks of length n have the property that they remain within about square root n distance of the origin. Okay? It's a very simple thing to prove. You can, if you don't know it, it's an exercise. But again, it defines for us a pseudo-random property. Almost all walks have this property, right? So it's a pseudo-random property of a walk to be homebound, to be close to the origin in this sense. Square root n distance after n steps. Okay, so just remember that. Now I want to tell you about a particular walk, okay? Like pi was a particular number in the normal numbers story, or TSP was a particular function in the P versus MP. So I want to tell you about a particular walk called the Möbius walk. And to define the Möbius walk, first let me define for an integer x, P of x is the number of distinct prime numbers dividing it, okay? And now mu of x, the Möbius function of x, of an integer x, is like that. It's 0 if x has a square divisor, if it's divisible twice by some prime. Otherwise, it's 1 if the number of prime divisors is even, and -1 if it's odd. And now, if you list all the integers, this Möbius function defines a walk for you. It's slightly different than the previous walk because you either walk up the street or down the street or stay in place. But let's extend it. Right, so it defines a walk, and you can ask whether this particular walk is pseudo-random in the sense we talked about, right? Whether it stays close to the origin or not. And here's a theorem. And this theorem is not difficult if you know the other definition of the Riemann hypothesis. But anyway, it was a very old theorem of Mertens. Following our equivalent, this walk, the Möbius walk, is pseudo-random. It stays close to the origin. And the Riemann hypothesis. So this question about the Möbius walk is equivalent to the Riemann hypothesis. I'm not saying it's the best way to solve it, but maybe it is. You know, we don't know. So this important problem is a problem about pseudo-randomness. It's a very natural property. Okay? Questions so far? Yeah.
What do you mean by a Boolean function is hard to compute? A random Boolean function?
Yeah, so a Boolean function on n bits, hard to compute, let's say, can be computed with in polynomial time or by a circuit of polynomial size.
So it's a circuit complexity.
Let's say circuit complexity, yeah.
So your pseudo-random sets are actually typical set in information.
Typical sets, yeah. They are typical sets. But there are various typical sets, yeah. Just large. Yeah. But I mean, in many applications, it's important to specify what they are. Unlike in information theory, just being large, right? But large is what I call pseudo-random, and then you want to know which pseudo-random property I'm talking about. If you are studying P versus NP, then it's hard to compute. If you are studying Riemann, it's homebound walks. It can be very, yeah. And with lots of applications of, the theorems are proved without proofs, you need to define pseudo-random properties different than that. I'll show you one more example. Okay, so I just want to tell you just the consequences of a lot of work starting from this subjective definition of randomness using pseudo-randomness into understanding what happens to all these applications of perfect randomness if we don't have randomness or if we have weak randomness. So these are the three possible worlds. We do have perfect randomness. We don't, but maybe the weather is unpredictable somewhat, or I don't know, stock market is unpredictable, etc. And the third world is where there is no randomness. So in the first world, we saw all these applications, wonderful applications. And it turns out that in a world without these, but with this, so all by, I'm not formally defining you what I mean by that, but what you should think about really is something like the weather, that you can sample it, and of course there will be correlations. You know, tomorrow's weather is a good bet to guess it will be like today's weather. So there are correlations. Of course, it's biased. You know, it's not like uniform. So events which have, so sequences or distributions of or sequences, let's say, of coins, but distributions which have some entropy in them, but not full entropy. They are not unbiased independent coins. What do you do with this type of weak random sources? And it turns out that's a very long work, that all the application which there is an algorithm, so any algorithm using randomness can be run with this type of weak randomness and have the same properties. This is far from, the way you are using the weak randomness is far from obvious, and I'm not explaining it. This has to do with the randomness extraction, and my one example will relate to that. It's a very, very long studied theory, by now very developed, and it's about basically converting weak sources of randomness into perfect ones. So I'll say something about this a little later. And the more challenging thing, it has to be more challenging, what do you do with all applications of randomness when there is no randomness? It turns out that here we need an assumption, but the assumption is not so bad. It's just that P is different than NP. It's not quite that. It's an assumption like this, but it's an assumption about the hardness of computing some explicit function or explicit functions. But if you assume that, so you just assume the computational hardness of the traveling salesman problem, and using that, you immediately get that all efficient algorithms, every efficient probabilistic algorithm, like all the algorithms I mentioned, like about finding primes or these domino tilings, all these algorithms which were probabilistic have deterministic counterparts that are not much slower. In other words, you can eliminate randomness from all these probabilistic algorithms essentially at no cost. All you need is one hard function. If you associate this problem with the P versus NP problem with the difficulty of finding needles in a haystack, you can interpret this as saying that if it's hard to find needles in haystacks, then it's easy deterministically to find hay in haystack. Anyway, this is another very long development, also over something like 30 years it took to understand. I'm not going to explain this, but it's another message you should take. In both these developments, it's essential to have a variety of pseudo-randomness definitions and replace two random bits with distributions that full weak computational devices. So it's very important to have pseudo-randomness for this purpose, various types of pseudo-randomness. So I want to show you just one glimpse of what goes in a special case of this result. Okay?
The thing, does it mean that there are some problems for which there is a randomized algorithm, but to come up with a deterministic counterpart would be as hard as proving P versus NP?
No, but it doesn't. But so maybe the question was not that. Okay, if I understand your question correctly, you were asking about possible converse of this theorem. Yeah. Okay. So in this case, the answer is we don't know. So what this says is computational hardness implies the ability to remove randomness from efficient algorithms. The question about the converse is we know this is a more recent study, and we know some things about it, but we are far from having a converse. It's possible that these seemingly unrelated problems are very intimately connected. This is one direction of the connection, and the other may be true also. In other contexts, we have a converse. Yeah, this is very interesting. So let me, more questions. All right, so let me tell you a little bit about this randomness extraction or purification. So again, it's the same picture. We have all these things we can do with perfect randomness, but reality provides us with, I don't know, poor ancient coins, not the gold coins. For what I'm going to do now, I'm going to assume that while each of these physical sources, like sunspots or stock market fluctuations, they may be correlated and unbiased in themselves. Maybe we have a few of them, and they are independent of each other, at least. That's what I'll assume, that there is no influence of sunspots on the stock market. Although, if you Google it, you will find that people believe that there is influence. Anyway, mathematically, let's assume we have a few sources of randomness. Each is weak, but they are independent of each other. Can you convert, maybe to fewer, maybe, can you extract entropy in sort of pure form of independent unbiased coins from such a few weak sources of randomness? So the answer is yes, and I want to show how it's done, which pseudo-randomness property goes into this area. I mean, actually, it's done in several ways, and there are better ways than what I'll show you, but this was the first way. So here the pseudo-random property will be a property of matrices, of tables, okay? So what is the property? Again, it will be defined by a bunch of conditions. You should think that I'm looking at n by n matrices whose entries are numbers between 1 and n, okay? Like in this case with 15. And the property I want to look at is saying that every small submatrix is just few rows and few columns. Every small submatrix has lots of distinct entries. Okay, when I zoom in here, so it's a 5 by 5 rectangle, but it has many more than 5 distinct entries. And this is true here, and not just consecutive ones. I cannot draw non-consecutive, but okay. So and it stands to reason that a random matrix will have this property. I didn't define small. I have the definition for small here. And this property is shared by most matrices. So let me state it. In a random matrix, every small window is rich in numbers, and namely have many distinct entries. We look at k by k. K you should think of much smaller than n. It's some small power of n. And if you look at a k by k rectangle, you see more than a linear number, more than k, like k to the 1.1 different entries. Why? We'll see why, but it's a property, and it's very easy to prove that this property is shared by most matrices. Okay, so again, we have a pseudo-random property here, and our objective is to find one explicit table that has this property. Okay, it's clear what the property is. Small submatrices are rich in distinct entries. Okay. So, well, which matrices, which tables do we know? I mean, you can, so we want to construct them deterministically, not randomly. Well, we can go back to second grade or first grade, I don't know when you learned addition, and you look at the addition table. That's a table. It's not quite, maybe the numbers are between 1 and 2n. It doesn't matter, but you can take all these numbers modulo n if you want. So the question is this matrix good? Is it pseudo-random? So some people are doing this. I don't see anyway. Is it pseudo-random or not? No, everybody's saying no. It's not, because, I mean, of course you see the diagonals are constant. So, if you take an interval by an interval or an arithmetic progression by an arithmetic progression, you will get just a linear number of distinct entries. So it's bad. Okay. And then you think, well, okay, but this was second grade. Probably we should do better. So in third grade, we learned about multiplication, and maybe it's better. Is it better? Again, you can take the numbers modulo n if you want, just to have the... Is this a better matrix from this point of view? Some brave volunteers say something.
Well, if x is a power of 2, it's bad.
Yeah, very good.
If n is a power of 2,
Yeah.
it's bad.
So if your submatrix is defined by a geometric progression, as opposed to an arithmetic one, then what happened above happens below, right? It's just, yeah. So it's bad. There are bad windows in this. So it's also bad. And so addition didn't work, and multiplication didn't work, and then you sort of remember this famous proverb of von Neumann saying, anyone who considers arithmetical methods in producing random digits is, of course, in a state of sin. So that's what it said. But I mean, those of you who know that he completely ignored his own advice and used arithmetical methods too. And that's what we'll do also. We will use these tables. And the way we'll use, so we'll forget his advice here. And the way we will use it is via really a remarkable theorem. I think should be taught in, maybe in high schools. But anyway, we learn addition and multiplication since we are kids, and we never think about it. Well, what is their relation? Of course, you get to algebra in college, you learn about fields, and but even then, what is their relationship? Are they, how friendly are they with each other? We learn the distributive law and stuff like that, but here's a statement that I think is really, really interesting and really, really useful. It's called the sum product theorem. And in this formulation, it says that if you look at these two tables together, and you look at a particular window, it will be reached either in the first or in the second, or in both. It will never be poor in both. So there's some independence of what sum and product do in this sense. Okay? You cannot have a set that when you add it every pair to itself and multiply every pair to itself with itself, you'll get a small set of numbers. One of them will grow in the exponent. That's the sum product theorem. And this is really good because having lots of numbers is more like having more entropy, and that's exactly the way it's used in this application. What we did in this old paper was take samples from a few different sources, which each has some entropy, and then you mix the addition and multiplication. You maybe add the first two and multiply by the third, and maybe this already increases entropy. You do it a few times, you can get your. So that's how this particular pseudorandom property was used in sort of a restricted form of randomness purification. Okay, so I think I just on time actually. Let me just summarize. So one message was that complexity theory view of randomness is that it's a subjective definition. It sort of depends on the computational power of the observer and not on the phenomena itself. We saw pseudorandomness, and there are many notions of pseudorandomness, and they usually correspond to what you want to do or what machines you want to fool. And pseudorandomness captures lots, really, I mean, I have no time to go into this, but lots of questions in math and in computer science are about pseudorandomness if you look at them right, and sometimes it's a useful point of view. The consequences I showed you, it seems that randomness is not as strong as it initially seems. If you ask me, I would say that, for the applications it's actually used for, it's not really needed. We just can't prove it yet. We need an assumption. And also pseudorandom objects, many of these works develop pseudorandom objects, and there are others that I didn't talk about, like expander graphs, hash functions, I mentioned codes. There are lots of pseudorandom objects that are useful beyond just removing randomness from algorithms. They are interesting for many other reasons. So this study is interesting in its own right. And that's it. Thank you very much.